Hi everyone, and welcome to my presentation. Today, we'll be taking a deep dive into sea level monitoring, exploring satellite altimetry and climate change impacts. We are going to start by looking at sea level monitoring and the key values scientists look for to identify variations in our oceans. Let's start by breaking down ocean topography to understand how sea level rise is calculated. These four values will be discussed in the following slides. Let's start with the geoid. It is defined as the equilibrium state of the ocean without any perturbations. This represents the state of rest of the ocean. Differences from the ellipsoid are due to local gravitational anomalies. These can be calculated and used by scientists for further understanding of oceanography. Next, dynamic topography is found by removing the geoid from the sea surface height. This leads to an understanding of the impact of ocean currents and thermal expansion. The dynamic ocean topography is highlighted as the red area in the sketch on the right-hand side of the slide. Finally, the sea level anomaly is calculated by finding the sea surface height and removing the mean sea surface height. It can be used to understand short and long-term patterns and changes in a local area. This helps the understanding of tides and weather events, such as El Niño and La Niña, which can induce regional changes in surface height. Next, we will focus on the use of satellite altimetry to measure, track, and predict sea level rise. Many satellites in orbit use altimeters, such as ISAT-2, Cryosat-2, and Sentinel-6. Satellite altimeters use waves in the electromagnetic spectrum to calculate distance, and therefore the sea surface height can be found. There are several types in use, but they all use the same principles. A reflected signal is received, and the range can be calculated assuming the exact position of the satellite is known. The range is calculated using the speed of sound multiplied by the time taken for the signal to return. The two main types of altimeters are radar and laser. They both use waves within the electromagnetic spectrum. However, radar altimeters use radio waves in the microwave spectrum and therefore are not affected by cloud cover. On the other hand, laser altimeters operate in the visible light spectrum and therefore are affected by thick cloud cover. This is due to their smaller wavelengths. Laser altimeters have smaller footprints, improving precision. However, technology such as SAR has been developed for radar altimeters to be more precise. A footprint describes the area that an altimeter will survey. Beam-limited footprints are often associated with laser altimeters. They are dependent on antenna beam width and orbital height. The diameter can be calculated using the equation in the bottom left-hand side of the slide. Using values found in scientific documentation for ISAT-2, the orbital height is set at 500 kilometers and the beam divergence at 22 microradians. We can then approximate the footprint to be 10.5 meters, and this is close to the actual value of the footprint being 13 meters. Synthetic aperture radar uses a combination of beams and pulses to create a high detailed survey of a precise area. SAR creates a smaller band of more precise information collected in the along track direction. SAR can also be further developed to create 3D maps, proving highly useful in multiple scientific disciplines. Ocean monitoring is essential for understanding ecosystems, changes in sea ice, sea level rise, and the global climate. Scientific understanding of the origin of sea level rise and its development has a direct impact on our climate models and prediction. This in turn dictates the actions that policymakers will take. I have broken down sea level rise into three main causes. First, the increase in the global annual mean temperature has led to the increase of ice sheets and glacier melting. This has contributed 1.8 millimeters per year between 2006 and 2015. Ocean thermal expansion has been an ongoing contributor to sea level rise. Between 2006 and 2015, it was responsible for an increase of 1.4 millimeters per year. Finally, changes in ocean currents and temperature gradients have greatly affected regional sea level rise. The global mean sea level has seen an increase of 3.6 millimeters per year between 2006 and 2015. With rates projected to reach up to 15 millimeters per year by the end of the century. The global mean sea level is projected to reach 0.39 meters by the end of the century. This number will grow exponentially for high emission models in the coming centuries. In 2100, the Greenland ice sheet is projected to contribute 0.07 meters to the global mean sea level rise. the Greenland ice sheet is currently contributing more to the sea level rise than the Antarctic ice sheet. Coastal areas are vulnerable to erosion, land loss, and flooding. These events are projected to significantly increase throughout the century under all greenhouse gas emission scenarios. Coastal cities around the world are at risk of becoming inhabitable, leading to large-scale migration, economic costs, and damage to livelihoods. Cities such as New York, Jakarta, and Mumbai are all at risk. Sea level rise threatens marine ecosystems such as wetlands, mangroves, and coral reefs. Almost all warm water coral reefs are projected to suffer a significant loss of area and local extinctions, even if global warming is limited to 1.5 degrees. Thank you for listening, and I hope you've understood sea level rise monitoring and its importance and impact on our planet.